So part 3 of this video set on IMFAs is going to focus on how we actually can predict the type of IMFA that a substance is going to form. First two parts we learned about the different types of IMFAs, what they are, what kinds of molecules have them. Now, how do we predict if the molecule is going to have that? So we're going to create a flow chart. So at the top of the flow chart is going to be the question, is the substance an atom or is it a compound? So you got to look at this formula and decide. If it is a single atom, that could mean that we could have metallic bonding. We could have, it could be a noble gas, or it could be another nonmetal, or it could be an element that forms a network covalent bond, like carbon or boron. If it's a compound, that's telling you that it's either going to be an ionic substance or it's a molecular substance. So it'll be either polar or nonpolar, which means now we're looking at London forces or dipole-dipole attractions and so forth. Or it could be silicon dioxide, which is the one molecular looking thing that forms covalent network. So once you know whether it's an atom or compound, it kind of splits up the possibilities in kind of half. Let's focus on this left side first. So if I know that it's an atom, I need to ask another series of questions in my head to figure out what kind of IMFA it's going to be. So let's ask an easy one. Is the atom a metal? If you say, yep, it's metal, what do we know then? The type of IMFA is going to be metallic. If you say no, then you've got to ask some more questions. So all the metals are going to be metallic bonding. If it's not a metal, then we've got to ask some more questions. Next question could be, is it carbon, boron, silicon, or germanium? Because those are the four that form covalent network that we've learned. We say yes, we know that it's a network covalent substance. We say no, then we got to check one last thing. Chances are it's going to be a London dispersion force, which means that it's either a nonmetal or as including the noble gases. So if it's a single atom that is a nonmetal, it's going to be London dispersion forces. So this side is pretty straightforward. Not a whole lot of work to do on your part in order to figure out what kind of IMFA it's going to be if it's an atom. If it's a molecule, however, if it's a compound, things get a little more complicated. So the first thing we're going to do is get the silicon dioxide out of the way. Is it silicon dioxide? We say yes, we know that it's network covalent solid. If we say no, we got some more questions to deal with, and these questions become a little more complicated. So, question number 1, is the substance ionic? So, what do you really need to know if it's ionic? If it's ionic, you better have a metal and a nonmetal there, or you better have polyatomic ions. So, you need to be able to recognize it as ionic. If it's ionic, we know that it's going to have ionic interactions. If it's not ionic, we know then that the substance is molecular. And this is where the work comes in. We got to do a lot of analysis of the molecule to figure out what kind of IMFA you're going to get. So I think the next question you should ask is the substance polar or is it nonpolar? And how are you going to answer that? So you got a lot of work to answering this question. You have to draw the Lewis structure. You have to think about the three-dimensional shape, and then you have to assign electronegativities, find any bond dipoles, and then determine whether or not you have a polar molecule or a nonpolar molecule. So this question is very loaded. There's a whole lot of work that you have to do in order to answer that question. But once you do, if you say, yes, the molecule is nonpolar, then you know that it's a London dispersion force. If it's a polar molecule, now you have to distinguish, could it have hydrogen bonding or not? So does the substance show hydrogen bonded directly to nitrogen, oxygen, or fluorine? If yes, you know that it's going to be hydrogen bonding. It's going to be that super duper type of dipole. If you say no, then you know it's just going to be a normal dipole-dipole. So normal polar molecules will just be dipole-dipole. Super strong polar molecules will be hydrogen bonding. And remember, this is the criteria for hydrogen bonding. So that's the flow chart you want to use. Hopefully you've filled out page 348, I believe it is. The back side of the organizer that we've been filling out has space for you to put this flow chart. So let's apply it. Let's do a couple of examples. Shoot, I didn't put any timing in on this. There's no animation. So all the answers are here. All right, so try not to look. So let's say that we want to know what kind of IMFA neon is going to form. So neon, we look at the formula, we know it's an atom. We follow the flow chart. Neon is not a metal, but we've come up with neon is a noble gas. So we know that there's going to be London dispersion forces holding neon together if we can get it cold enough or compress it enough to form a liquid or to form a solid. The attractions that hold those atoms together is going to be a London dispersion force. Let's look at our second example. What type of IMFA are we going to get if it's CH2Cl2? Dichloromethane would be the name of this. So we look at it, obviously it's a compound. It is not silicon dioxide. It's not ionic. These are all nonmetals, so we know it's not ionic. Now you've got to draw the three-dimensional shape. We know it's going to be a tetrahedral. These two bonds are going to be nonpolar, carbon to hydrogen, but carbon to chlorine are going to make it polar. Since 2 of the 4 bonds are going to be polar, we know that overall the molecule is going to be polar. And so we know it's going to be dipole-dipole because hydrogen is not bonded directly to oxygen, nitrogen, or fluorine in this molecule. So we know that it's going to be dipole-dipole. So that's how you want to approach answering a question like that. To know what kind of IMFA, you've got to kind of work through the flow chart that we developed. So now it's your turn to practice. You've got some problem sets to do.